So what we talk about in physics are we call them free body diagrams, but a lot of things that are static, things that are not moving, right? You have forces acting on these things. Mostly gravity, things that are overcoming gravity. Maybe I'll get my, this mouse is coming in. What's that? Oh yeah. Yep. Well, the floor, right, is holding the table, right? The table's holding my book. And there's lots of forces. If we, no, I won't mess with that. Here we go. Here's a good example. Okay. So you have a vector pointed down, straight down, right? And you have two vectors that are each pointed in the direction of these wires. Yes? Right. Now, in this situation, right, you have you still have two vectors coming up, and you have one vector going down. What do you think the lengths of these vectors would be compared to the length of the one going down? Think about half. Because this wire has to overcome half of the weight of this, and this wire would have to overcome half of the weight. So you'd have two short vectors and then one long vector, right? Now, tell me what happens to the lengths of these vectors. Tell me what's happening to the lengths of these vectors. Are they still half? You think they're getting longer? So these vectors are now pointed in this direction, right? So do you think they're getting longer, shorter, or are they staying the same as they were here? Longer? Well, they're both getting longer. Longer? What's going to start to happen here? What's going to happen here? What's going to happen here? Help me out here. This is getting difficult. Why is this getting difficult? No, I'm talking about the vectors, though. What's happening to the force I'm applying here? Each arm is applying half the force to overcome the weight of the bottle, right? But as I start to do this, okay, because I'm changing the direction of these, I'm trying to overcome the weight, and I'm having to apply more and more force. It's actually impossible for me to get this completely horizontal. It is impossible for me to do that, okay? Not with just these two wires. This wire will break before. Trust me, I could break the wire. No. I couldn't break this wire if I wanted to. But I could keep applying a force no matter how hard I pull. Those vectors can get longer and longer. It's impossible. Now, we can show it mathematically why it's impossible. That's why everything, you're going to have a sag in every structure. There is a sag. Have you ever seen those big trucks that, transport stuff, 18-wheelers? Some of them are built with a bow in them, It's because there's always going to be some sag. Anyway, okay. I'm just trying right now for you to understand the idea of why vectors are important, because the position of them doesn't matter, right? If I'm in the room right here doing this, or if I'm over here doing it, or if I'm over here doing it, this doesn't matter, right? Doesn't matter where I am in the room. These things still have the same definition. They're still equivalent to one another. So it allows us to move around. There was something else I was going to talk about. Some people don't believe that I'm applying a force to this. I've heard that before, like, you're not applying a force to this. Does anyone have a doubt?
You're fighting gravity, so you have to be applying.
So everyone's okay with that? All right. If you ever run into someone who's like, no, I'm not applying a force, just tell them to do that, and then just come lift the book up real quick, and you'll see their hand go up. And then you can say, well, why was your hand moving? Because you're... Yeah. But I do have one more demonstration. This is off topic. But while I've got a book out and I've got you curious... It's going to get loud. Going to drop these. Ready? So, Who's going to hit the ground first? Ready? Do a mental guess. Ooh, I told you to be loud. Okay, so the book hit the ground first, and my question is why? So everybody's got an answer as to why? So it does not have to do with the weight of this book. It does not have to do with the mass of this book. It has nothing to do with that. All right? In fact, the only reason why this one hits the ground after this one does is because of air. If the air was not here, well, then we wouldn't be here. But if the air wasn't here, then they should hit the ground at the same time. And if you don't believe that, I can prove it to you right now. I will take the air out of the room. All right, so here, check this out. If I put this paper on top of the book and drop them and look up, there's no glue up here or anything like that. If you believe that it has to do with weight or mass, then what should happen is the book should drop away from the paper because it's going to drop faster. If that's what you think is happening, it's because of mass. Then this should do this, right? Well, like a reverse sort of, yes. But if I drop them together, they go together. And the only reason they went together is because the book is moving the air out of the way, and so there is no air to slow this down. So they go together, right? Kind of interesting. You know that when we got to the moon, if you believe we got to the moon, some people don't even believe we got to the moon, but when we got to the moon, they went out there, hopped around, and they dropped a feather and a hammer. Did y'all ever see that video? They did that?
They did another experiment where they actually had like a vacuum chamber.
Mm-hmm.
They dropped a bowling ball on a feather.
Mm-hmm.
They all just fell exactly at the same speed.
Yeah. That's a science project I was going to do with my daughter, but they didn't have a science fair this year. So you can make vacuum chambers pretty easy. Yeah. You got to be careful though, because if you use glass, you can like implode it and stuff and hurt yourself. But okay, so the scientists actually when we got to the moon, went to the moon and actually took a hammer and a feather and dropped them together, and they fell at the same time. That's because the moon doesn't have an atmosphere. They had already proven that a long time ago, so it wasn't like it needed to be proven. They were just kind of like, we told you. Because there was a big problem with like theology versus science, and you know, the earth is flat versus round, earth is the center of the universe versus the sun is the center of the universe, or you know what I'm saying? So when they got to the moon, they're like, yeah. It's like a mic drop, I guess, you know, up there on the moon with a hammer and a feather. Okay, I am way off. Let's go. Two vectors are equivalent if they have the same length and same direction. Yeah? All right. Sound like Chewbacca. That did, right? Kind of. I just heard it in the background. All right, so let's now talk about some properties of vectors and when it comes to addition and multiplication. Adding vectors. I won't call it that. Let's just do it. Okay, so let's say we have two vectors and we want to add them together. Let's say we have the vector v and we want to add it to the vector u. What does that look like geometrically? Let's see. So I'm going to come up with two vectors. I'm going to make them up. Let's say this is the vector u, or v. And then let's take another vector u. Let's put it over here. Let's make it shorter. And let's make it point in a different direction. These are not equivalent vectors, right? They are not equivalent. So what happens when we add these two vectors together? Geometrically, what happens? Well, what we do is we slide the tail of one vector over to the tip of the other one. Now remember, vectors are equivalent so long as they're pointing in the same direction and have the same length. So you see this vector u? If I take that vector u and just slide it over like this, it's still the same vector. If I move it up a little bit, it's still the same vector. So what I'm going to do is I'm just going to move it appropriately to where the tail of this one lines up with the tip of this one. Right? Then we have this. That and this. And again, it doesn't really matter where they are anymore, right? Because they could both be moved around. That's the picture we would have, right? Now what we do is we draw a new vector, and that new vector is going to go from the tail of v to the tip of u. So that vector, I'll do it in red. This vector right here is the vector v plus u. Does v plus u have a direction? Does it have a length? Yes, right? Its direction and length are not this, right? This is not the same direction as v. It's not the same direction as u. They don't have, doesn't have the lengths of either one of those, but it has a new direction and a new length, right? So that red vector is v plus u. So what I said is to take v and add u, what you do is you take the tail of u and attach it to the tip of v. Tail of u to the tip of v. Would it have mattered had I done it the other way around? Curious. What would happen if instead of doing the tail of u to the tip of v, I did the tail of v to the tip of u? So imagine taking this one, taking that and then kind of like moving it up and then moving it over, and what would we get? Let's see. I'm going to try and do it right here. If I let u just sit there and I brought the v over, like that. You see how that's a different picture? Then the result would be starting out at u and going from here to the tip of v. That would be that red one right there. This would be u plus v instead of v plus u. Are they the same? Do you think they are? My drawings suck, okay, but do they seem like they are? It's the same thing. It is the same thing. I might be able to illustrate it better if I asked you to take this picture and just move it down here. In other words, transpose this picture like that. That's this side and this side. If you take that and bring it down like that, we would have the same vector either way, right? The red vector would be the same. So because of this, vector addition is what we call commutative. It does not matter which order you do it in. And the result is you get this picture, no matter how you do it, you get this picture that kind of looks like a parallelogram. And so this is called the parallelogram rule for addition. What I want you to really remember is that when you add two vectors, it's tip to tail or tail to tip, however you want to look at it. Tip to tail, tail to tip. That's how you add two vectors together. Okay? All right, next thing is what does scale, I'm going to get to subtraction, but I want to talk about scalar multiplication of a vector. Scalar multiplication. What do I mean by scalar? What's a scalar? Anyone know what a scalar is?
It's the opposite of vector. It's just the magnitude.
See, scalar is weird because it confuses students. A scalar is a number, like a real number, like 3. Or 5? Or pi? A number. A scalar is a number. Is a vector a number? No, a vector is a directed line segment, right? It's this object. So what this is about is what happens when I take a number and multiply this vector by this number? What happens to the vector? That's what this is all about. So, for example, let's say we take c and we multiply it times the vector v. So c is a number. All right, what happens to the vector? That's the question. So I'll tell you what happens. If c is greater than 0, which means it's positive, and c is greater than 1. Now I know this is kind of obvious, like if it's greater than 1, it's greater than 0. But just stick with me on this, right? So let's say that c is greater than 0, so it's a positive number, and it's bigger than 1. What do you think it's going to do to the vector? So what if I take a vector and I say multiply it times 2? What do you think it's going to do to it? Double it. How do you mean double it?
Make the same vector twice.
Twice.
Like 2v.
Yes, but geometrically. So here's that vector v. I say 2 times v. What is it going to do to it? Is it going to change its, do you think it's going to change its direction? No? You think it's going to change its length? Yes, it's going to double the length. All right? So if you multiply by a number that's bigger than 1, a positive number bigger than 1, then c times v is a stretch of v. All right, it's a stretching out of v by a factor of c. So if you multiply by 2, it's going to double the length. If you multiply by 10, it's going to 10 times the length, right? That's what happens if you multiply by a number that's bigger than 0 and bigger than 1. How do you think I can shrink it then? Like if I have a vector, it's this length, and I want to make it maybe half as big, I mean, you multiply by half, right? That means I do need to multiply by a positive number, but not by a number bigger than 1, by a number smaller than 1. So I can say if c is between 0 and 1, right? Between 0 and, so this was saying, look, I'm bigger than 0, but I'm also bigger than 1. This is if it's between 0 and 1, then c times v is a, what, compression or something? Shrinking of v.
Can you divide vectors? Or just multiply by the same?
I'm glad you're asking. Do you mean divide it by a number?
Yeah.
Okay, so the question that's being asked is, can you take like the vector v and divide it by 4, let's say? You just look at that as being 1/4 times v. So division is really scalar multiplication. Does that answer? What is a more profound question is, can you divide a vector by another vector? Right? Can you take the vector v and divide it by the vector u? Can you multiply 2 vectors together? Like take a vector, take another vector, multiply them, and get an answer.
Yes.
What is it? I mean, you know?
The length of, or like, I guess the length of one would add with the other.
Yeah, so it actually turns out to be tricky. It turns out that if you have 2 vectors and you want to multiply them together, we actually have 2 different types of multiplication. So this has never happened before. Like with numbers, if I say, hey, take 4 and multiply it times 8, you don't ask me, like, which multiplication do you want me to do? Like the regular multiplication or that other multiplication, right? Everyone's like 4 times 8 is 20, obviously. Right? So 4 times 8, that's no problem. But with vectors, take 2 vectors and multiply them. There's 2 types. Dot product is one of them. and the other one's called the cross product. So there's two operations for vector multiplication. That's not what we're talking about right now, though. We're talking about scalar multiplication. What happens when you take a vector and multiply it times a number? Okay? Next class, well, I don't know about next class. We will do dot product in this class. We will not do cross product, because cross product is three-dimensional, and we don't go into 3 dimensions. So, all right, so y'all understand the scalar multiplication? Yes? Okay, now one more thing. Let's start this over. What happens, scalar multiplication still, what happens if I multiply this by -1? What is -1 times a vector? What does that do? What do you think it does? Turns it over the other way? So like if it was pointing like this and you multiply it by -1, it's now going to point in the opposite direction. That's exactly what happens. So this right here flips vector in opposite direction.
Does the notation change as well?
No, you just write -v. So -v, like here, look here, we can do it right here. See this? There's v, right? If I just flip it over and point it the other way, that's -v. And that doesn't even have to be there, right? I could like slide it over here and put it over here, and that would still be -v, as long as it was pointing in the opposite direction. Yes?
So we multiply by like -3 or change the direction and the length?
Okay, so yeah, now if you can extend this now, if you now do multiplication by -3, you're going to flip it and stretch it out by 3. So we can combine those two ideas together now, and we get what is basically scalar multiplication. What happens if you multiply by 0? Curious. What is 0 times v? What is 0 times the vector v? Zero? Okay, so we need to cover just a real quick little technicality here. All your life, all the arithmetic you've ever done has behaved very well. In other words, if I take two numbers like 5 and 2 and I have you add them, you would get 7, right? So two numbers added together, you got a number. Two numbers subtracted, you got a number. Two numbers multiplied, you got a number, right? Dog and a dog? Huh? Dog, right? Cat and cat? Cat. Yes? This is weird. What we're doing here is number with vector. Number with vector, and it's spitting out vectors, right? Number, vector, vector. Number, vector, vector. That's what's happening here. All right, there's no way around it. That's what's happening. So if I do number, vector, and I want to follow what's been going on, the answer to this better be a vector. So it can't be the number 0, or it doesn't fall in with everything else that's been going on. So, but it should be 0. So how about the 0 vector? I didn't hear you. I'm sorry. I didn't hear you. Speak. You got it? 0 times any vector is the 0 vector. So the 0 vector is not the number 0. That's like calling my cup a dog. They're not the same thing, right? 0, well, I mean, nowadays, right? You can be anything you want to be. I should probably shut up. I'm going to just stop right there and stop right there. I have long conversations with my good buddies about being careful about what I say on camera. Okay. Let's scalar multiplication. Just one visual representation because we didn't do subtraction, right? We didn't do subtraction, so let's just do a quick subtraction. So let's stick with these vectors right here. No, I'll start with two new ones. So I'm going to draw a picture here. You kind of do your best to draw a picture here. Let's call this U. You know, the sad thing is I may have really offended somebody with what I just did. Like, it is possible that I could have really offended you. And if I did, I'm sorry, I didn't mean to, but you know, that's where we are, man. It's like, because maybe one of you really does feel like a German Shepherd, and now I've insulted you, making light of it. I'm not. If you feel like a German Shepherd, then good. Good for you. I just see someone like, no, never mind. Okay. I know, man. It's gonna get bad. It's gonna get bad. So what would U minus 3v look like here? I want us to graph this vector.
So, will we not have to like?
So let me help you with this. How about this? How about if we look at this way? U plus negative 3v. How about we look at it this way?
So we're going to flip it the other direction and extend it by 3?
Yeah, so why don't we take the v vector, let's flip it over and stretch it out by 3. Okay, let's do that first. So I'm going to take the v vector, I'm going to flip it and stretch it. So here's how long it is, right? Which, you know, you use something to measure it, whatever. And then I'm going to flip it the other direction, so I'm going to do 3 of these. There's 1 of them, 2 of them, about 3 of them. I think that's about good. Would you all agree that's negative 3v? Now, I'm supposed to add that vector to u. So I go tip to tail, or tail to tip. And I told you, because addition is commutative, it doesn't matter which tail goes to which tip. So I could move this over and attach it here, or I could move this one and move it up to there, or I could move them both around as long as I don't twist them and change their directions. Y'all with me? So why don't I just move this red one over, slide it over. It almost lines up perfectly. So I'm going to slide that over. Maintain that same length. I think that's about it. Agreed? I'm getting sloppy with my notation here. And lastly, where is the vector that represents u minus 3v? Where does it go? Tail of u, the tail of u, to the tip of that one up there. So it's from here. Totally missed it. Totally missed it. That's it right there. This is u minus 3v. And then I can move that black one around anywhere I want, up, down, left, right. Just don't change the direction, don't change the length, and that is the vector. Now, I know we're almost out of here, and I know you want to go. I do too. But let me show you a picture now of me holding the book. There's the book, right? Here was that vector coming down, which was gravity. We call it the gravity vector. I should actually call it the weight vector, because it's not gravity, it's weight. Let me do that, weight. Okay, and then my hand was pushing up, right? So that vector is actually pointed up like this, right? And because the book was not moving, These have the same length, don't they? So I'm going to put, I'm going to call this one R for Robert. Okay, that's me holding the book. So what can you tell me, what's the relationship between these two vectors? Like if the book wasn't moving, what's the relationship? Okay, are they equal? They're not quite equal. W would be equal to negative R though, wouldn't it? Do you agree with that? This is this vector switched directions.
What happens when you multiply two different vectors together? You end up getting that.
It's a little more complicated when you do, well again, there's two types of multiplications, but when you multiply two vectors together, you multiply their lengths, and then you also multiply their cosine of the angle between them, which, yeah. Okay, so what I'm trying to get you to see is this. This is a relationship we have, right? Just geometrically. What would W plus R be? If you take this vector and you add that vector, you go tip to tail to tip, right? So if I took W, then I took R, and I moved the tail of R to the tip of W, what would happen? It'd be here, right? Wouldn't it? Be like this. And then your result would be starting here and then ending here, which would be the 0 vector. Do you agree? That's the 0 vector. And if you move the R over, you get this again, right? So that was me holding the book. Now look at this. This is me with this thing, holding this, right? Had the two pieces, the two wires. So I had two vectors. I had one vector that went like this. I had one vector that went like this, right? Now let's just call this vector R1 and call this vector R2. Here's the way, this is the direction we're headed, all right? Here's where we're headed. What we're going to do is this. When I'm holding this wire, I still want to get out of here too, don't worry. But when I'm holding this wire, there's no motion, right? It's not going up or down, it's not moving left or right. That means that whatever forces are acting straight down have to be countered by the forces acting straight up, right? And whatever forces are moving left have to be countered by the forces moving right. So take a look at this vector right here. See that vector here? I could actually recreate that vector by going and taking this vector and adding this vector. Do you see that? This black vector is the purple plus the blue. Yes? Also over here, this vector is this purple one plus this blue one. Got it? So what do you think the relationship is between this purple one and this purple one? Not equivalent.
It's a 0.
They add up to be 0. In other words, whatever this vector is, this is the same vector but negative. Because these are the only forces that are moving left and right, right? So they have to counter each other. So the force that way has to match this one. What about the force going down versus the forces coming up? These two blue ones together, right? If I slide this one over like this, move this one up and over, that has to match the length of the one going down. Agreed? This is what vectors allow you to do. Now, what happens when I start to pull? When I started to pull?
Starting to stretch from the center. So like the purples are extended.
So as I did that, here's the picture, here's down. That doesn't change, right? That vector's very, But as you start to stretch this thing out, this picture, let me draw a dotted line. Missed it. Okay, there we go. Okay, so let's say I try and pull this almost horizontal. When I do that, these two vectors, the black ones, like this, right? Like this. When I break down the blue parts, look how small these blue parts are now. See how small they are? Right? See how small they are? So the only way to counter this downward purple is with these two little blue ones, right? The only way I can make those blue ones longer is by making this vector longer. And to make this vector longer means I have to pull harder. Okay? Because this is gravity, right? And I'm trying to offset it. Do you imagine if I move down, come off camera, this thing keeps going, right? Then eventually that blue over here, together with this blue over here, will counter that purple. But the more I pull, the shorter this becomes. Do y'all get that? So you cannot, look, if it was horizontal, if it was flat, if it was completely flat, then you don't have blue vectors going up, do you? And if you don't have blue vectors going up, you can't counter the force going down. It's impossible, unless it's rigid. I mean, if it's rigid, of course, there's bridges, right? But those are rigid. This was not rigid. So this is an impossible scenario to do that, to get a cable with a weight, pull it, and get it straight. Not going to ever happen. You're always going to have some sag to it. All right, we will do more vectors. At least do all your homework for law of sines and cosines. The test on Thursday will have some vector stuff on it. All right? That's a long class. Does that seem long? That seemed long. You're all, yeah. Oh my God. Get the hell out of here. Let me turn my camera off real quick.